Hi, my name is Will, and today I'll be presenting this work, Adaptive Sampling Strategies to Construct Equitable Training Datasets. And this is joint work with Ro, Bobbie, Sam, Miranda, Stevie, and Sharad. The idea behind polygenic risk scores is to use genetic variants present in one's DNA in order to predict risk of disease. And you can imagine that this could be a really powerful public health tool if it worked, right? Because you could focus interventions on people who are at high risk of certain diseases. One issue in deploying these scores to the entire population is that these scores often perform much worse in populations of African ancestry versus those of European ancestry. And a lot of this is thought to be due to lack of representation in the training data. A recent study of the genome-wide association catalog, where the data to train polygenic risk scores comes from, finds that 78% of individuals in the catalog are of European descent versus only 2% of African descent. And that's obviously a huge gap. And so this lack of representation is leading to worse model performance for people of African ancestry. And I'll note that this problem is not contained only to polygenic risk scores, right? There have been analogous examples in a wide variety of domains and also across a wide variety of subgroups defined by race, ethnicity, language, and nationality, right? So this problem of lack of representation has led to a call within the computer science and machine learning community to diversify datasets. And that's kind of the starting point of this project. We wanted to, motivated by this, we wanted to discuss what a fair training dataset might actually look like. And so I think typically when people think of fair training datasets or fair sampling, they'll think of a few popular heuristics for sampling. So for example, things like equal or representative sampling. But what we find is that depending on the circumstances, these heuristic strategies can lead to unintended consequences. So for example, representative sampling by default oversamples from majority groups, right? That's what it means to sample representatively. You sample more from the group that has more people, which we think is a funny thing to encode by default as a sampling strategy. And further, even something like equal sampling might sample from groups which already have high model performance and whose model performance does not increase with additional samples. And thus, you're kind of wasting resources by using this sampling regime. Okay, and so given that these heuristic strategies might, not work in all situations, the question becomes, what do we actually do? Okay, and so to make this more concrete, let's talk about an actual problem that someone sampling data for a polygenic risk score might face, right? So we extend a simulation created by domain experts, which allows us to simulate human genomes and actually train polygenic risk scores with different sized data sets of different composition between race. And so say concretely that we start with 500 samples from people of European descent and 500 samples from people of African descent. And further, say that we have an additional budget of 4,000 that we can use to sample, and so we can sample people of either descent. And so the final allocation is going to be something like 2,000, 3,000, which represents 2,000 people of European descent and 3,000 people of African descent, or 4,000, 1,000, anything that adds up to 5,000 and has both of them bigger than 500 is a possible final allocation. And the question becomes, which allocation do we choose? And so our approach to deciding this is a two-step process. And the first step is to model what we call the learning curve, which is the mapping from the dataset composition, which is something like 2,000, 3,000, to group level model performances, which is the model performance in people of European descent and people of African descent. And the second step is for the model builder to specify their preferences over resulting group level model performances into a single utility function. And then given these two objects, the learning curve and the utility function, our approach is to optimize over all possible data set compositions to maximize this utility function. And so, in some settings, if you have a global understanding of the learning curve and it satisfies, certain geometries, you might be able to use tools from convex optimization to do this. In our setting, we consider a setting where you can sample in an online manner, right? So you can sample one batch of people, update your model, and then use that information to decide who to sample next. And the methodology we use for doing that in this setting is Thompson sampling. And so that's our approach to deciding which allocation one should choose in this setting. Okay, and so let's look at what that might look like. And so before we talk about any sampling strategies, we can talk about a performance trade-off. And so here on the y-axis, we have the model performance in people of African descent. And on the x-axis, we have model performance for people of European descent. And the reason there's a trade-off between these two is that we have a finite budget, and depending on which group the budget goes towards, which group gets more samples, the model performance for that group might be better. And so that's why there's this trade-off, as you might expect. And then now we can look at where our heuristic strategies land us on this trade-off. And what we find is that, as we alluded to earlier, representative sampling is doing something a little bit funny, where it's going down this steep trade-off, right? The steep part of the trade-off curve, and which means it's trading off a large amount of performance for people of African descent, for only modest gains in model performance for people of European descent. And the reason for that is because, these two heuristic strategies don't take into account model performance at all. They're just sampling purely based on heuristics of the overall population. And so because we place the setting in the United States where there's more people of European descent, we actually just oversample from that group and end up making this trade-off. And here, equal sampling finds a point on the trade-off curve that's a little more reasonable. But you can imagine, again, because it's not something, it doesn't take into account what this curve looks like, what this trade-off looks like at all. You can imagine, depending on the geometry of this curve, that it might also end up on a very steep or a very flat part of the surface, which is something we want to avoid. Okay, and so now we can compare this to our adaptive sampling strategy. And so remember, the model builder has to specify a utility to use our strategy. And so one reasonable starting heuristic as a utility function is to just say I care about the model performances equally, so I'll let my utility function be equal to the sum of the two model performances in the two groups. And what you get when you specify this utility function and run the Thompson sampling is something here. And we can see that our adaptive sampling approach has found a point that's close to this, ideal trade-off between the two groups, where the model performance is getting traded off at a rate of 1:1. And the reason it's on the inside is because of this curve is there's some loss due to having to learn the learning curve and use kind of a noisy estimate of that to do the sampling. Okay, and finally, the last thing I'll mention here is that our approach allows for a very easy way for a model builder to intervene efficiently and make their model more inclusive for a group that's been traditionally underserved by simply upweighting that group in the utility function. And so here in utility priority, we upweight the model performance for people of African descent by 1.5. And what that means is that, the allocation we find moves to the upper left. And, as you expect, because we upweighted how much we care about model performance for people of African descent. And further, we find that in this setting, the two points are relatively close. And the reason for that is we specified we're willing to trade off model performance at a rate of 1.5:1. But as the adaptive sampling strategy moves to the top left, the cost of obtaining additional model performance from people of African descent becomes more costly than a ratio 1.5:1. And so it's no longer willing to trade that off and go further up to the left of the curve. But you can imagine, again, depending on the geometry of this trade-off, these two strategies might actually be quite different. in where they end. Cool. So to summarize, what we hopefully showed is that a lot of fairness work has considered this setting where you start with a fixed data set, and then you decide how to either train your model or how to modify your predictions in order to guarantee certain statistical criteria related to fairness. What we showed here is that by intervening at the data sampling stage, before the fixed data set even comes into the picture, we can efficiently construct inclusive models that lead to more equitable outcomes. And at an even higher level, there's many potential intervention points, beyond just the data sampling stage in the model building process, where similar interventions might similarly lead to more equitable outcomes. And we hope that our work is part of the push towards exploring these all these potential intervention points. And finally, the last thing I'll say here is that throughout this work, it was quite useful to formalize preferences into a utility function because it allows us to apply techniques from optimization and move beyond heuristic strategies for sampling. Obviously, this is going to be quite difficult to do in a real setting, right? It's difficult to go to a stakeholder and be like, put your utility function down in math. But even something like the utility equal that we started with can be a useful starting point to get something reasonable, start sampling in a reasonable manner, and then refine what's going on from there. And finally, looking forward to the future, we worked with one particular type of model in our setting of these polygenic risk scores. And I'm quite curious what these learning curves might look like for different types of models, and how how that would affect how we implement our adaptive sampling strategy. So for example, for things like deep learning, it might depend on how many samples you need from a group in order to get your model working reasonably for that group, whether you can get away with, whether you need the same number of samples per group, or you can, with just a few samples per group, if you can fine tune your model to those samples in order to get high performance as well. And I think, one potentially really interesting direction for this work is to add an active learning component that not only chooses what data points to label or sample based on which group the data point is from, but also the covariates associated with that data point. Cool, thank you.